Ladies and gentlemen, welcome to this lecture on smart charging of electric vehicles and on vehicle-to-grid. The following questions will be explained in this lecture. What is smart charging and vehicle-to-grid, and why do we smart charging? What are the advantages and disadvantages of vehicle-to-grid? And finally, in which cases can smart charging be applied? First of all, let's look at the definition of smart charging. Smart charging is a series of intelligent functionalities to control the electric vehicle charging power in order to create a flexible, sustainable, low-cost and efficient charging environment. Smart charging has several benefits and has a huge potential for the future. For example, smart charging can increase the flexibility of charging by controlling the charging power, charging time duration, and charging power flow direction. With the high charging flexibility, the utilization rates of fixed assets like transformers and power lines can be higher, which also helps in reducing the cost of electric vehicle charging. Smart charging can increase the efficiency of power transfer and help to reduce the power demand on the distribution network. Further, electric vehicles can be made more sustainable by charging them based on solar and wind generation. Moreover, smart charging can provide new revenue streams to electric vehicle owners, like providing frequency regulation and vehicle-to-grid services. In order to understand the concept of vehicle-to-grid, let us look deeper into it. Vehicle-to-grid refers to the concept of using the electric vehicle battery to feed power back to the grid. In order to facilitate vehicle-to-grid, we need bidirectional electric vehicle chargers that both draw and feed power between the electric vehicle battery and the grid. Besides the grid, the battery power can flow from the vehicle to a home, to a building, to a load, etc., and it is called V2H, V2B, V2L respectively. V2X is the generic term that is used to include all such applications. There are a number of key benefits of V2X technology. First of all, it enables the storage of electricity in the car, especially from renewable sources, which leads to emission reduction. Also, by using the stored energy, the peak demand in the electricity grid can be reduced. Next to that, electric cars can now serve as an essential system component in an emergency power supply. Lastly, ancillary services can be offered to the grid using an electric car with V2X configuration, providing a revenue stream to the EV user. At the same time, a number of main challenges for V2X are identified as well. First, V2X needs bidirectional chargers, which are bigger and more expensive than unidirectional chargers. Secondly, the lifetime of the battery inside of the electric vehicle is partially reduced, since the bidirectional charging demands more charging cycles, causing additional degradation. Further, the ICT infrastructure, the required standardization and regulatory framework and financial incentives, which are essential for the implementation of V2X, are still under development. Finally, it is important to note that vehicle-to-grid is currently not possible using AC chargers due to the technological limitations. This is because a bidirectional onboard charger is needed for vehicle-to-grid, but most current electric vehicles only have a unidirectional chargers which are on board. Further, V2X requires higher levels of communication between the electric vehicle and charger, and this is not fulfilled by the simple pulse width modulation communication in Type 1 and Type 2 AC chargers. Hence, bidirectional off-board DC chargers are used for vehicle-to-grid applications using higher level of communication between the electric vehicle and charger using PLC, power line communication, or CAN, control area network communication. With a basic understanding of smart charging and vehicle-to-grid, let us now look at a few examples to understand the application. First, smart charging can help in balancing the local load, and this can be done in two ways. Shift the charging time slot according to the loading on the grid, or by balancing multiple charge points with priority. Second, smart charging can increase the utilization and subsequently the installation of renewable energy sources in the grid. Third, the smart charging can facilitate charging based on the electricity prices in order to reduce the charging cost. Apart from that, the smart charging can be applied to peak shaving and to provide backup services for the grid. The last three examples are specifically applicable to vehicle-to-grid. Let us now look at the smart charging applications one by one. The first load balancing approach is to shift the charging time slot and to adjust the charging power based on the grid capacity and local loading conditions. For example, when the load on the grid is low, the EV charging power can be increased. Alternatively, if the load power increases, then the EV charging power can be subsequently reduced. Finally, the electric vehicle charging can be stopped if the grid is overloaded and remain so until the load power is back to normal. With a limited maximum power for charging the cars, smart charging can sequentially operate multiple charge points with priority, or adjust the power of each charging point so as to be within the maximum limit. With the smart charging, each car can also be charged with different strategies according to the load and the priority. Smart charging can help in controlling the charging power of the car based on the renewable energy production, say from solar and wind generators. Here in the example, we can see that smart charging power, the dotted blue line, is an envelope of available solar generation in red line and wind generation, which is in green line in this picture. Further, with V2G, the electric cars can be used as massive energy storage to balance the variable generation from renewable energy sources. Next, we look at the price-based smart charging. Here, the charging power is increased when the electricity price is low, and the charging power is decreased or even stopped when the electricity price is high. Further, customers can get more profit when V2X is applied. For example, we can charge the cars when the electricity is cheap, as it is in the smart charging interval, and discharge the car via V2X when electricity price is expensive and above a certain pricing level, as it is in the V2X interval. In this case, the X of the V2X can be home, building, or the grid. In case of peak shaving, the aggregated electric vehicles can work as a mass storage in the grid. With control charging, the electric vehicles can be charged when there is an extra renewable energy generation, and they can discharge via V2G to feed the grid when there is a peak load in the evening. By doing so, the peak of both generation and consumption can be shifted, and the electric power demand-supply gap can be perfectly matched. In the future, electric vehicles can even operate as a backup for the grid on a relatively large scale. In case of a short duration failure, electric vehicles can be connected to the grid, to our homes or to loads, and can be controlled to provide emergency power via vehicle-to-grid. To wrap up, you have now got an idea of what is smart charging and the key role it can play in the future smart grids. Vehicle-to-grid is a special case of smart charging where the energy from the electric vehicle battery can be used to feed power to homes, buildings, and to the grid. We looked at some examples of smart charging to see how the electric vehicle charging can be controlled based on renewable energy generation, energy prices, grid loading, and how the electric vehicles can be used as a storage and as an emergency power supply. Thank you.